Well, good morning, and there's a question for you. If you're trying to think about it, you know it's wrong. You have to draw a picture. I don't expect you would always do what the mug tells you to do, right? You have your own mind. So, a question, I guess, basically about what does every circle have? So there's the particle, it travels and approaches the region with the magnetic field, enters the magnetic field bends the trajectory. We don't care what's happening, actually. Eventually it leaves. But when it enters, the magnetic field, magnetic force starts acting on it. Force is a vector, always has a specific direction. And we have 6 standard directions: up, down, left, right, into the screen, out of the screen. Standard choices. Is it about right-hand rule? No. Has nothing to do to right-hand rule. It's about force bending the trajectory of a particle. This ball would have been traveling just straight down if it wasn't for the force of tension bending the trajectory, make it bend. And same is true for that circulating particle. It circulates. So let's see. Oh, I can't see it. Oh, Ariana Grande is here to save us. Interesting. Why me? That's lecture number 11. Summary. I believe some students should say, oh, there's no I was late. Okay. That was PY105. So we have a distribution. And the 4 is the correct answer because, again, it's not about magnetic field or any other field, or right-hand rule or left-hand rule. It's about how force changes velocity, and for a circular motion, when trajectory is a circle, the acceleration, which changes the velocity, has to point toward the center, hence the force will point toward the center. And for that location, that means to the left. Well, that was a review. So we have to solve this problem. We started it, and we have established the fact that magnetic field should point out of the screen. So basically, it's not one problem. It's just 3 problems, almost independent from each other. The only connection is same magnetic field, and also we can see the radius. So that the strategy always follows same steps, free body diagram, etc. So let's just do it. But first, I want to use some kind of a systemic representation of everything we may know about particles. We have 3 particles, A, B, C. A, B, C. For each particle, we have what? We have given parameters: mass, charge, speed. Then we can calculate the period. Well, actually, first probably acceleration, force, period, kinetic energy, and then maybe same variables using different equations. So, and of course, we start from free body diagram. Well, free body diagram for each picture, for each particle is really simple. For example, here, right now, we have a force pointing down, force on C. When this particle enters magnetic field, force action on it points to the left. That was the question we have answered. And this particle enters field, and the trajectory is bent down, so the force has to point down. And for each particle, we can write the same equation, F equals, well, first of all, we can always write first the expression for the magnitude. That's a Lorenz's force. It equals Q, V perpendicular, B. But in this problem, as in many other problems, velocity is perpendicular to magnetic field, so we don't have to use that symbol. Magnetic field points out, and all velocity does just points in the plane of the screen, so it always remains perpendicular to the direction out of the screen. And acceleration equals v squared over r, and Newton's law says F equals ma. Kinetic energy equals mv squared over 2, and a period, well, this is how I prefer relate them. And so 1, 2, 3, 4, 5 equations for each particle. So 5 times 3, 15 equations. And we will do that. But also we need to look at the information provided to us. So what do we know? Well, for particle A, we know that its mass equals 4 times, and that little m represents some kind of a factor. Could have been kilograms, could have been tons, could have been milligrams. So this information only tells us how to relate the masses. For example, particle B has the same mass as particle A, but particle C has an unknown mass. So this is one of the variables we will have to figure out. Now, there are different ways to do that, and I prefer to write this unknown also in terms of that variable m, because it's supposed to be canceled eventually. So the particle C is x times heavier or lighter. So this is what we are actually looking for this factor. It's going to be a number. So particle C has mass of, well, a certain number times this factor m. What number? I don't know, 1, 2, 3, -7. Well, can it be -7? No, mass cannot be negative. All right, so what do we know about the charges? Particle A also is given in terms, for the particle A charge is given in terms of some factor. And B, that's an unknown, and another unknown. So we don't know QB. So again, we can introduce some factor and calculate the charge of particle B in terms of that factor. And particle C has a charge Q. So particle 2 has charge twice of the particle C. And particle B has charge Y times of the charge of particle C. And before moving on, we have to say something about this charge. We know that particles A and C are positive. Now, you have to figure out QB. Well, it's a number, so as for any number, it could be positive, 0, or negative. So I'm going to give you a time to figure it out and make a statement. This basically will tell us if this coefficient, a number, y, will be positive, negative, and of course it can't be 0. Why? What would happen for a particle if the charge would have been 0? It wouldn't circulate, it would just travel through magnetic field without being affected. No charge, no force. So if it's not the case, it's not 0. Wrong. We are eliminating wrong options. That's what science does. Now, if it's a positive particle, you would have to use the right hand. If it's a negative particle, you would have to use the left hand. And we can make an assumption and see if that assumption would work. That's the direction of velocity. And magnetic field points out of the screen. So if I use the right hand, the force acting on this particle would bend it up, would make it move clockwise. That's not the case. So right hand rule doesn't work. That's a negative particle. Which means this coefficient technically should be negative. All right, what do we know about velocities? They're all given. V, and C travels 4 times faster. Now this is the acceleration. Well, acceleration. V squared over r has to be written 3 times for particle A, for particle B, for particle C. So of course, how do we write it for particle A? This is how we write it for particle A. And this is how we write it for particle B. And this is how we write it for particle C. We just use a subscript which corresponds to the particle, but that's not informative, so we have to go further. A has a speed of v, and the radius, well, the radius is the geometrical feature. The trajectory, which we see, is a semicircle. That's the center. So the radius r is equal to 1 block. We can use it as the original value of a radius. For particle B, we actually have exactly the same speed and exactly the same radius. Well, actually, you see, it will immediately tell us the charge of a particle B. If you look at particle A and particle B, same mass, same speed, same magnetic field. Okay. Particle C, for particle C, speed should be equal to 4 times of speed of particle A. And the radius now is not just 1 r, but 2 r's. Actually, this is what I should have here. 16 over 2r, bless you. What information can we extract? Well, for example, acceleration of particle A is equal to acceleration of particle B, but acceleration of particle C will be equal to 8 times acceleration of A or B. So we don't know actual values, but we know ratios. For example, if I want to calculate AC over AA, the answer is 8. Or else? See, no thinking, just following equations and pictures, that's it. Force. For particle A, the charge of the particle is 2 times factor. Speed is v. Magnetic field is the same for all of them. For particle B, we don't know the charge, but speed is the same. Magnetic field is the same. For particle C, we know the charge, and the speed equals 4 of the speed of A, and same magnetic field. So what does it give us if we want to? Well, yeah, it's hard to see where is a Q and where is a 9. The answer is no 9s. There are no 9s, at least so far. So, well, I can see, for example, the force acting on a particle C will be B and B, V and V, Q and Q, 4 over 2, 2 times stronger than the force acting on particle A. Well, the period. For each particle, the period equals the ratio So here it's 2 pi r over v. Here it's 2 pi, same r, over v. Period for a and b is the same. And here, where is it? C. 2 pi, 2r over 4v in terms of r's. Of course, as we know, when we don't have specific values for specific variables, that means they don't matter for our analysis. So if we're not familiar or not very confident with algebra, we could set m to like 1 kilogram, q to 1 coulomb, r to 1 meter. That wouldn't affect ratios at all. But using algebra is kind of good exercise. So now what I can immediately say, for example, period A and period B are equal to each other. How can I use it? Well, I can prove that particles A and B, mathematical proof, should have same magnitude of the charge. Well, but for that I would have to now use a different expression for the same period. That expression comes from solving these equations. We did it yesterday. You know what? I'm going to use this space. I'm going to do it one more time because that's important practice. So Q V B is equal to M V squared over R. That gives speed and that gives the period. There's one thing I want to fix because breaking rules is wrong. And I broke a rule which says don't use the same letter for different variables. Capital R is set for a specific distance. It describes, for example, the radius of a circle for particle A. So I cannot use the same variable for any generic radius. So that's why I have to use lowercase r for that. Now I can start again. Q, V, B should be equal to M, V squared over R. So Q, B, R over M is equal to speed. And now the period will be equal to 2 pi R over speed Q B R M. So R and R cancels. But we can use this expression twice. First time for particle A, 2 pi. For the particle A, the mass is equal to 4 times that factor m, and we have to divide by the charge of that particle, which is given in terms of Q, and magnetic field. For particle B, what should we write? 2 pi. The mass is 4 times m. Now, the charge of the particle B is that unknown variable, but we use the factor to describe that charge times B. And now, of course, we can see, we have proved mathematically after canceling out everything we can, magnitude of that factor y is equal to 2. We knew it from the picture. You know, same mass, same field, same charge. And the final answer is y equals -2, it has to be negative. The charge is negative. Now, what else we need to figure out? X, yeah, I forgot. So for that, we need to relate particles A and C. And I have no space left. So this is what I want to write. Again, if I look at the periods, we can make a conclusion that the period of C is equal to, so please tell me, in terms of the period for particle A, what should I write? They are not equal. So one period should be larger, maybe twice larger, maybe 3 times. So another period should be less, like a half or third or a quarter. And this is the most important statement we have to make right now, because after that we know what to do. So how do you relate the period of particle C and the period of particle A using that information? Yes? Yep. 2 divided by 4 is a half, so 1/2. That's it. Now you just have to write the same expression here and there using actual values in terms of given factors. And for particle C, this variable m should be equal to unknown factor x times m. See how many m's. And every time when we write it, we need to know what it represents. And the answer will be x equals where is it? It should be 1. Yes, right here. As after we plug it in, everything getting canceled. So the factor x equals 1. And of course, you can repeat the same type of reasoning for anything you may need to do. Kinetic energy, acceleration, everything is based on exactly the same strategy. Newton's law, centripetal acceleration, Lorenz's force. That's it. Any questions? So if you don't have a question, I do. In this example, what we have a positive charge, maybe a proton traveling through 2 fields simultaneously. The electric field is presented. That's the electric field. And as we remember, electric field exerts a force on a charge. And if it's a positive charge, the direction of a force is the same as the direction of the field. But the particle travels straight ahead, which means there has to be at least another force which cancels the electric force. We neglect gravity, we don't see strings, no friction. We actually create by our own hands magnetic field which exerts a force in the right direction with the right magnitude. So the net force acting on this charge is equal to 0, and charge travels straight ahead. And the question is, what is the direction of magnetic field? So This is a combination of Newton's law, because net force equals 0. And of course, right-hand rule, this is a positive charge to relate the direction of the field, the direction of velocity, the direction of the force. But if you need to relate field, velocity, and force, and you see velocity, how does velocity point? To the right. You also need to draw a vector which represents magnetic force. How does magnetic force point? What do you think? If we had two forces both pointing down, it would bend like a ball, making a projectile motion. Because that's what the gravity does. And if this is not happening to the charge, what's happening to the charge is something like this. So, how does the force point? The force which cancels electric force. If it would be pointing to the right, it wouldn't cancel electric force. It would still move, well, like this. You have to cancel electric force. To cancel electric force, no. No, keep going. Up is correct. It's exactly the same situation. There is force of gravity, but normal force cancels it out. So that's the first statement we have to make. Magnetic force, not magnetic field. Magnetic force has to point up. Plus, it cannot be too short. It cannot be too long. Or we should say, it cannot be too weak or too strong. It has to have exactly the same magnitude as electric force. But that's the force. By the way, we can write that magnetic force and electric force have exactly the same magnitudes, right? And by the way, the expression for magnetic force, everything is perpendicular to everything, QVB. The expression for electric force is QE. Turns out we can cancel out the charge. Turns out for any charge, positive, negative, doesn't matter. As long as speed has a certain value, which is equal to this ratio, charge will travel not affected by the fields, like they just don't exist. But the speed of this charge must have exactly the right value. So now, finally, we can apply the right-hand rule, right? So this is the force, this is the velocity. How does magnetic field point? Oh, I had a slide. Into the screen. So, what's going to happen if the speed of a charge is different from this value? Well, let's say that the speed of a charge is less than this ratio. That would make magnetic force weaker than electric force. So electric force would have been stronger, and the charge would travel like this. Trajectory would have been bent in the direction of electric force. What would happen if the charge would be traveling faster? In that case, magnetic force would have been stronger, and the charge would have been deflected again. And if we had a charge catcher here, photoplate, for example, these charges would miss it. So only those charges with that specific speed can travel through this device. That's why this device has a name, a velocity selector, because by manually changing magnetic field and electric field, we can set speed to the value we want and have only charges traveling at that speed passing through this device. And what can we do next? Well, then we can generate another magnetic field, just magnetic field, and that particle now, with a known speed, will travel through magnetic field bent, and we can catch it somewhere. And if we catch it here and we know it enters there, we know the radius. So if we know magnetic field because we manufacture it, if we measure the radius, if we know the speed, this experiment tells us how to calculate this ratio for each particle. And then it's much easier to actually measure a charge separately, independently. And if we measure charge, we can calculate the mass. That's why this device has a name, mass spectrometer. That's how all masses for all particles, all known elements have been measured very accurately. And also, this is how right now Hadron Collider in Switzerland working. They just use much more energetic particles. That's how the Higgs boson was discovered. And this is an actual photograph one of our professors shared from Hadron Collider. Well, and finally, what will happen if a particle is entering magnetic field at certain arbitrary angle? In that case, of course, because of the perpendicular component, it circulates, but the component which is parallel just makes it move. So in the result, it travels in a spiral. And when a very energetic cosmic particles enter magnetic field of the Earth, they start traveling like this. And when they do that, they emit light. And that's what you see, North Pole lights, South Pole lights. All right. We saw once that electric current is acting like a magnet. It affects a magnetic needle. In fact, let's say I have a very, very famous physical device. How do we call it? Black box. So, and I have a magnet outside, and that magnet registers the presence of magnetic field. What is inside? And actually, we cannot make a conclusion until we open it. It could have been another permanent magnet. But it could have been certain manufactured in a certain way, wire, maybe in a very complicated way, wire connected to a battery. They both generate the same type of field. So we call it magnetic only because originally, thousands of years ago, people knew only permanent magnets. But now we know electric current acts like a permanent magnet as well. So, of course, we have to, well, first I want to check one more time if it still works, hopefully. So what do we do? Works, still works. Physics always works if you do it right. So I connect a battery to this, well, it's a coil set of loops, and we can see it creates a magnetic field actually in a specific direction. And we can see the direction. And there is a rule, of course, which relates the direction of electric current with the direction of magnetic field it generates. But this is a more complicated situation. First, we start from much simpler situation. A straight wire. Straight wire generates the easiest magnetic field. Well, we gotta see it. You know what? We're gonna see it here. All I need is a power supply and a wire. So here I have one single loop, a coil, and this part represents a straight wire which goes right into this plastic surface. And now I need a power supply, and I have to connect the power supply. And how do I do that? I have to use wires. And I always have to use red and black, right? No, the color doesn't matter. I'm not hiding. I'll be back. I just need tiny, tiny compasses which magnetic field will affect to make them move in a specific way. And we've seen those tiny, tiny compasses yesterday in oil. We call them iron filings. But now we're going to use them again, like a salt shaker. And okay, let's bring to focus. All right, maybe more. Why do I need to knock? The friction wouldn't prevent them from moving, and they've been moving. Actually, maybe it's clearer here. Yep, actually. They make circles around this wire. All right, since I'm on this, let's check all others. This is a single loop. This is a coil or solenoid. So I have to reconnect the wires. We can see shapes of magnetic field lines, but so far no information about the direction. old equipment. All right, so here, again, here, of course, around one part of this loop, we have circles, other circles, and then lines go outside, larger and larger. Well, let's see the last one. Maybe it's too much. Okay, now current, red to red, black to black. Does it matter? No. Well, that's the best picture so far. But yeah, you can see how lines go inside and outside. This actually very similar to magnetic field of a permanent magnet. In a permanent magnet, of course, magnetic field inside exists. We just can't see it. Here, we can see it. And inside the solenoid, magnetic field lines practically parallel. So this is another way to create a uniform magnetic field. Just have a long coil, long solenoid. And we will have an equation for that field. All right. Here, yeah, very nice lines. Well, that's not the only experiment. Now we have to talk about the direction. We see shapes. How to relate the direction? Well, we have to have a more accurate measuring device when we can see the direction. Let's have several compasses. Now we have to connect. So this is a straight wire, and we know now from this experiment, magnetic field created by this wire should be circular, like this. You just have to imagine the same wire was here vertical, like this, and that's what we saw, circles. And now we have to use our ability to manipulate with mental objects to turn it around and still see the same circles. And this ability to visualize things which don't exist, very important. And that's what makes, for many students, this part of this course harder. However, I would think it's easier than, for example, for a doctor to look at this picture, at the photograph, at the scan, and visualize actual organs and parts. So you can consider all this physics as practicing in visualizing things which you cannot see. Now, what happened? No magnetic field, no electric current, no magnetic field. I can do it this way. Turn it on. And now they all aligned. So magnetic field here generated by this wire is circular. And well, it brings us to another right-hand rule. If you use the right direction of electric current, okay, so plus electric current goes that way. So if you imagine that you're grabbing the wire with your palm in such a way, so the wire is inside the palm, inside, not outside, that's wrong. And the finger points in the direction of electric current, in that case, the thumb. In that case, these curled fingers will show you the direction of magnetic field around the wire, everywhere. Here it points down, here it points away from you, Here it points up, here it points toward you. It's a circle. So, and this is north, this is south. Inside of the magnetic field points from south to north. It's called the north. It goes out of the north. So this is how we relate the direction of electric current, and it actually becomes warm. Yeah. I basically shortened the power supply, which provides 5 amps, which is relatively high current. So now we can go back to math. Math, not math. We don't do that in physics. So that's the right-hand rule, which has been proved. Every time when you need to make a statement about a direction of magnetic field generated by a straight wire at a certain point, you have to use that rule. You have to imagine you're grabbing the wire, point thumb in the direction of the current, fingers show you the direction of magnetic field lines around it. So now the question. We just have learned this rule. Let's practice this. Red arrow represents electric current traveling in this wire. Magnetic field created by this current is everywhere. Here, 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 behind the screen, everywhere. To measure that magnetic field, we take this device and just walk around and we place it and see how does it point. And when the needle is in equilibrium, we look at it, direction inside from south to north tells us the direction of magnetic field, but now we can use the right hand to apply another second right-hand rule. In physics, there are many right-hand rules. And question 4. Come on. Oops. Who answered question 6? Well, I assume it was a mistake, an honest mistake. 5 is into, and into is correct. So if I imagine, well, I have to imagine. I cannot put my hand behind the screen. I would have to cut the screen here and there. So I have to imagine that I'm doing that. And then by doing that, I'm directing my fingers here inside the screen, into the screen, there, out. Here, at this location, magnetic field would point like this. Next question, just one more to practice. Here, this red dot represents a wire which is horizontal and which goes right to you, and electric current travels out of the screen toward you. That's the direction of electric current. So right here, we can measure magnetic field. That's exactly the same location, but instead of having wire diagonally, placed, we switched it, we turned it. And that should affect the direction of the magnetic field it generates at the same point. it might be helpful sometimes using actual arrows. So in the previous example, that's what was happening. Current, magnetic field. And what are we doing now? We're turning the wire, but the magnetic field has to be consistent with the direction of the current. So they fixed together. And of course, here, if we use the right-hand rule, magnetic field lines generated by a current should be circular. So this is one specific magnetic field line. Now, it's a circle directed, so it has a direction. How should we draw an arrow which represents the direction? We have only two options, clockwise, counterclockwise. In this situation, this is, according to right-hand rule, counterclockwise direction. And if we move away from a wire, that doesn't change the shape of the lines, it's still circular. That doesn't change the direction, still counterclockwise. But magnetic field strength decreases. We know how. And if I want to draw a magnetic field vector, all I have to do is just draw an arrow which tangent to line. This is magnetic field vector, this is magnetic field vector, this is magnetic field vector. But it is hard to draw a perfect circle, as you can see. That is why there is a better approach, which doesn't require drawing circles. What does every circle have? Center and radius. We can see the center, we don't see the radius, but the radius actually a much more useful geometrical device, because for every circle, if we draw the line which represents the radius, it has to be perpendicular to the circumference, to that line. So that's the most convenient approach. So what do? Well, I draw the radius of that imaginary circle which represents magnetic field line. Well, that magnetic field line exists. I don't have to see the whole line. I only can see a small portion of that. I also have to see the direction. The direction is counterclockwise. And now all I need to do is to draw an arrow which is perpendicular to the radius. That automatically will be tangential to the line. That's it. So that's 5. Yes. If I want to draw a magnetic field vector at a different location here, what do? Same approach. I draw radius first. Oh, okay. Of that line. Then I have to make a statement about the direction. For that, I have to use my right-hand rule. And my right-hand rule says right here, magnetic field lines points, again, counterclockwise if we complete the whole circle. But all I need is just one vector perpendicular to this radius. That will be magnetic field vector. That's it. That's how it works. So, and well, this is an equation for magnetic field strength. And I'm just going to give you, again, a minute or two just to practice. Electric current has a 5 amp strength. Distance equals 1 meter. The permeability of free space, this constant, has a fixed value. All you have to do is plug the numbers in and calculate the strength. What is the direction of magnetic field? We know magnetic field points like this. which means if I have a compass placed here, it will have this orientation in the direction of magnetic field. So actually, I don't remember the answer. So let's see, 4 pi 10 to the negative 7, 5, 2 pi, 1. Pi and pi cancels forward to 2 times 5, 10, 10 to the negative 6. And that is 1 micro Tesla. But of course, the situations we are interested in involve several sources. In the past, we had a situation when several charges created an electric field that we had to calculate the net electric field. Now, when we talk about magnetic field, a different source, a wire, creates magnetic field. If we have two sources, each source creates its own magnetic field, so we have to calculate the net. This is a standard example. So what do? We use the same approach we used before. For each source, we have to draw a vector which represents its individual field, and then we have to add them up together. So I'm going to, again, give you a minute or two. You have to draw two vectors. One vector should represent magnetic field from the first wire, and second vector should represent the magnetic field from the second wire. Where? Here at the same point, because that is where we should add them up. And again, we almost always choose from 6 standard choices for a direction. It could have been up or down, right or left, into the screen or out of the screen. So for magnetic field number 1, what direction should I choose? No? What direction for the magnetic field number 1? Correct? Into the screen. So it is, again, kind of hard to do with the hand, but we have to practicing in doing that. The thumb points to the right. We have to imagine there is a wire in our palm, and magnetic field lines at the point P go straight away from us. So B1. What about B2? What do you think? If you think it's you, it's you. What do you say? What does she say? Yes. Out of the screen. Thumb, fingers, and right here it will be out of the screen. And for out of the screen, what do we use? a different symbol. Technically, all these three symbols, yeah, the dot, so the dot, point P, the cross for magnetic field in, and the dot with a circle with magnetic field out should be at the same location, but we wouldn't be able to see anything. So that's why we kind of space them around, but in our mind we need to understand they are at the same location. Now we know what to do. We can calculate the magnetic field strength number 1. Now, what do we know? We know that this combination of variables is 10 to the negative 5. So just to simplify our calculation, and the distance is 30 centimeters, 0.3. And B2 is different because electric current number 2 is twice stronger, higher. But if the distance is the same, B2 will be twice stronger or twice higher than B1. So 2 times this factor. So what do we do now? Well, B net is equal to B1 plus B2, 10 to the negative 5 over 0.3, plus 2 times 10 to the negative 5 over 0.3. I was waiting for this opportunity for so long. Yes? Because I do what I want. You're approaching the right situation, but with the wrong attitude. You're just asking. If you're sure, you don't ask, you just tell. So, no, let's try again. So you should say, well, I don't know, Mr. V, you made a mistake, you have to fix it. And you have to explain what a mistake. Mistake is a wrong sign. Why? Because vectors have directions, and it's an easy fix, actually. We have to, well, normally, if you remember from PY105, when we use the Cartesian system, XYZ axis, the positive X direction chosen to the right, the positive Y direction chosen up, and the positive Z direction is out of the screen. That's a standard choice, standard agreement. So relative to this standard agreement, into the screen means a negative number, and now we're subtracting 2 minus 1, 1. So 10 to the negative 5th over 0.3, negative. What is it? Actually, times 10 times 10, 10 to the negative 4 over 3. So 10 over 3, what, 3.3 times 10 to the negative 5th Tesla. So we have reviewed basically how to add vectors. Yes? No. Now you are wrong. Yes?
What was the at 10 to the minus 5t?
Meter. That's just a SI unit for this combination. We assume using international system of units automatically for everything. This is Tesla times the meter. All right. That was a question. All right. I'm going to give you a minute or two to answer this question. In this situation, we now have 4 wires with identical electric currents, but the current number 3 points differently from currents 1, 2, and 4. These 3 point out of the screen, and this one points into the screen. So your goal is to make a statement about the direction of net magnetic field at the origin. And of course, you have to just repeat the right-hand rule 4 times. First, you have to draw 4 arrows for the magnetic field number 1, for the magnetic field number 2, for the magnetic field number 3, for the magnetic field number 4. Then you have to look at them and add correctly, like vectors. So you do your part, and I'm going to start from doing my part. Wire number 1. So electric current number 1 points out of the screen. The location where we are calculating magnetic field is right below it. So first, what I want to do, I want to draw a radius of that imaginary circle, which would represent the magnetic field line, because I know my magnetic field will be perpendicular to that radius. And perpendicular means, in this particular case, left or right. I have to make a choice. And to make a choice now, I can apply the right-hand rule, because current points out, direction of lines should be counterclockwise. Right here, counterclockwise means this is the arrow I should choose and use. That's B1. So the right-hand rule was used to make a statement about the direction of all magnetic field lines. All right, moving on. Current number 2 still points out of the screen, but now the same location relative to this current will be to the left to this current. Does it affect the direction of magnetic field lines? No. Magnetic field lines still are counterclockwise. So still have to draw a little circle to make a statement about the direction of magnetic field lines. Now we can draw the radius of a larger circle and draw an arrow which represents the magnetic field number 2. Has to be perpendicular to the radius, has to point down like all vectors which are straight to the left to the wire. Also, we could do this. I'm not hiding, I'm just looking for electric current. That's electric current. Now, that's magnetic field. I'm moving electric current. If I move it to the right, magnetic field moves to the right. If I move it to the left, magnetic field moves to the left. But if I move it like this, making a turn, magnetic field has to make the same turn. They are coupled. So now, number 3. It points into the screen, the same location, but now it's above. Now, the right-hand rule now says that magnetic field lines will be clockwise. So if I draw perpendicular, the arrow should point to the right. That's B3. And the last one. Four arrows. Now, of course, we have to draw them together. One. So, because all distances are equal and all electric currents are equal, that means the magnitudes of each magnetic field also are equal, which means the one which points up and the one which points down cancel each other out. So the net magnetic field points to the right. Plus, in this particular case, the magnetic field strength of the net magnetic field will be equal to 2 times any individual magnetic field. That's it. Now, again, just for quick practice, same arrangement, but we can see that electric current now is different in different wires. So how does it affect the situation? Well, the direction is the same as was before, which means the direction of each individual magnetic field is the same. 4, 2, 1, 3. What is different? Well, this wire and that wire carries the same current, same distance. So this magnetic field has the same strength as this, still cancel each other out. So the net magnetic field in this situation, again, is just B1 plus B3. And all you have to do is just calculate them together. So B net 4 pi 10 to the negative 7 times 30 amps divided by 2 pi times 2 meters plus 4 pi 10 to the negative 7 times 10 amps divided by 2 pi times 2 meters. In this simple example, both components are positive, we just add them up together. And that will be Tesla. Well, this is a physically easier, mathematically more complicated situation. Why is it physically easier? It has only 2 wires, not 4. Why is it mathematically more complicated? You have to draw a picture. So, right here, the location at this location, how does magnetic field number 1 point? We know how. How does magnetic field number 2 point? We know how. That's it. Now we can see what's going on. If we have to calculate the net magnetic field, we have to add them together as vectors. So this arrow plus this arrow, or together, this red arrow will represent the net magnetic field now. Well, now we know what to do. We have to use the Pythagorean theorem. And if we need to describe the direction, we have to use a tangent. Because tangent just will be equal to, that's B2, that's B1, B2 over B1. And the strength of the net field will be equal to B1 squared plus B2 squared. That's it. If you cover the wires, you don't see anything new anymore. The source doesn't matter. The physical nature doesn't matter. It's a pure trigonometry, which has been done many, many, many times before. This one, also very similar to calculating the location where a satellite experiences zero net gravitational force or a charge experiences zero electric force. So now we need to find the location where net magnetic field will be zero, which means if we place a wire at that location, it will not experience any force. Well, of course, we have to start from analyzing magnetic field from a wire 1, then magnetic field from a wire 2, and then figure out where they could cancel each other out. So magnetic field due to wire number 1 is represented by circular lines with a clockwise direction. It always is helpful to draw first one line which represents the direction. And magnetic field generated by the second wire is represented by circular lines which are counterclockwise. Counterclockwise. So let's see, for example, what's going to happen in the middle. Right here, magnetic field number 1 should point straight down, but magnetic field number 2 should also point straight down. So they will be impossible to make net field be equal to 0 at that location or anywhere between. So we have to check two other natural choices, to the right of the system, to the left of the system. Well, to the left of the system, magnetic field number 1 should point straight up, and magnetic field number 2 should point straight down. But magnetic field number 1 will always be stronger because it's closer to the stronger current. So what's left? Here, to the right of the system, magnetic field number 1 points down, and magnetic field number 2 points up. And technically, there could be a certain location where they have exactly the same magnitude. That's exactly what we are looking for. So let's say I set this distance to an unknown. That's what I'm looking for. I know that right here, right now, magnetic field strength number 1 should be equal to magnetic field strength number 2. So this is how we calculate magnetic field strength. We can cancel constants. Now, each wire is located 2 meters from the origin. So this distance is equal to 2 meters. This distance is equal to 2 meters. So, 30 divided by, what is the distance from the first wire to the location we are looking for? It should be equal to 2 meters plus 2 more meters plus x more meters. 20. What is the distance from a second wire? X, we called it x. Now we just have to do simple math. 30 times x will be equal to 20 times 4 plus x. And as you can see, this is not a quadratic equation. So it's much easier to solve than we had to do it for gravitational field or for electric field. So what does it give us? 1.5x equals 4 plus x. 0.5x equals 4. X equals 8 meters. Well, wherever it is. Any questions? I'm going to save this because it's not related to any calculation, but I still have 1 minute. Actually, when my alarm goes on, after that, I still have 1 minute. All right. So I'll see you tomorrow. Don't forget about the lab. And I'm going to go to my office hours right now after leaving this room. So if you have any questions, we can meet there.
I just have a small question. Can I ask now? Okay. So if if a current has magnetic field, then if we only have like an electron moving